Okay, today we're going to be talking about enthalpy and calorimetry. Now recall these are our problems from our last class. Chemical systems have enthalpy, and recall from our previous class that we did talk about the internal energy available to chemical systems. And as we look at a definition for enthalpy, enthalpy is equal to that internal energy plus pressure times volume. And enthalpy would be a state function, that is, it would be independent of pathway. And also it's true that internal energy, pressure, and volume are all state functions as well. So let's talk about what happens in a chemical process, say a chemical reaction that you're carrying out in the lab. We need the pressure to be constant. That pressure can be atmospheric pressure, and that's generally assumed to be constant during the relatively short time period of a chemical reaction in the lab. So all work is done then by pressure and volume using the equation that we talked about last class, work being equal to the negative of pressure times the change in volume. Now I'm going to go through a lot of equations relatively quickly, but recall that you can rewind and go over these an additional time if you need to. So we're going back to a definition of energy as being equal to heat times work. And so looking at that as a formula, we have delta E equals Q sub P plus work, and the sub P references that we're looking at heat at that constant pressure. So what I'm going to do now is simply substitute in our equation for work. So where before we had plus W, we now have minus P times delta V. And then I rearrange the equation so that we have that measure of heat as equal to energy plus work. We can also consider, remember that our enthalpy we said was heat plus work, which means in our change in enthalpy would be our change in heat plus our change in work. And again, we stated that our conditions are going to assume pressure to be constant, so we can remove the change in sign from pressure, and we now have the equation delta H equals delta E plus P delta V. So we've actually created two identical equations. One is an equation we defined as being for heat being equal to the change in energy plus work. And then we've defined another equation where the change in enthalpy is equal to the change in energy plus work. So in other words, those are two equivalent equations, and we can say that the change in enthalpy is equal to heat. So just looking at that in words, we're saying that at a constant pressure, the change in the enthalpy of a system is equal to the energy flow as heat. We talk about energy flow a lot because that's something that we can measure. So the heat of a reaction is equal to the change in enthalpy, again, under those conditions of constant pressure. And if we're measuring a change, we always note that change is equal to final minus initial, or in this case, the change in enthalpy would be that enthalpy of the products minus the enthalpy of the reactants. Okay, so now let's look at the two possible cases. We can have a positive result. When we take products minus reactants, we can have a positive result. And that would indicate three things: that the products have greater enthalpy, that heat is being absorbed, and that the reaction is therefore endothermic. Okay, and we could obviously have the opposite case. We could have a negative delta H, and that would mean that reactants have the greater enthalpy. That would mean that heat is being released, and that would mean that our reaction is exothermic. So you have some problems with regards to this. Please note that in order to do these problems, you're going to need to remember how to do mass mole conversions. And in a quick explanation is that the mass of a substance times 1 mole over the molar mass equals the number of moles. So this is something you may want to go back and review if you don't recall how to do mass mole problems. Okay, so let's move from enthalpy to calorimetry. And calorimetry is the science of measuring heat based on observing temperature change when a substance absorbs or discharges energy as heat. So we're moving a lot in here more and into a lab method, which recall we do have a lab that we're going to be conducting later using calorimetry and using a calorimeter, which is a device to measure, i.e. determine experimentally the heat associated with a chemical reaction. So let's look at some of the basic ideas that make it possible for us to carry out these kind of experiments. And one of the things that we need to recall is that substances respond differently to being heated. So this means that one substance may take a lot of heat to raise its temperature, say by 1 degree, while another substance is going to raise its temperature by 1 degree with just the addition of a small amount of heat. So if we think about something like a cast iron skillet versus silicon that's used in heat mitts and that kind of thing, some things are going to heat up easily, some things not so easily. So we're going to say that heat capacity would be the heat absorbed divided by the increase in temperature. And as you look at your book or potentially other books, you'll notice there are different abbreviations for heat capacity. In this class, we will try and keep it at a consistent C. And another way to think about this is it's going to take a lot more energy if you have more of a substance. And I think that you can, just if you think of something like a small pot of water versus a large pot of water, it's going to take a lot more energy to boil that large pot of water. Okay, so heat capacity again, heat absorbed divided by an increase in temperature. But we need to factor in when we're just talking about that idea that it's going to take more heat if you have more of a substance. And when we factor that in, we develop something called the specific heat capacity, typically, but not always, indicated by a small letter C. And specific heat capacity is when we look at heat capacity per gram of substance. This allows us to more readily compare different substances. And let's look at the definition of specific heat capacity then. Another way to say it would be that that is the energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. And it's important here, just for a minute as an aside, to consider that you could also be measuring things in Kelvin, and the same definition would work. The magnitude of a degree of Celsius and a degree and a Kelvin would be the same. That's part of the basis of that system. Their values would be different, but their magnitude would be the same. So when we look at the units then for specific heat capacity, we have units of joules. That's our energy measurement divided by degrees Celsius times grams, or alternatively you can use joules divided by kelvins times grams. Specific heat capacity can also be measured based on moles, and we use the subscript M to indicate that. And so C sub M would be a measure of that heat capacity per mole, or if we want to put it in words, that would be the energy required to raise the temperature of 1 mole of a substance by 1 degree Celsius. And then quickly just looking at what the units look like. The units now look like joules divided by degrees Celsius times mole, or in other words, joules could be divided by Kelvin times mole. So specific heat capacities, you can imagine, are known values. And on page 254 in your text, you have a very small chart of some of the heat capacities. The one that we're going to use the most and that is often used in experiments would be the specific heat capacity for water as a liquid, which would be 4.18, and that's the value in your upcoming lab. So as we develop enthalpies using the equation that we talked about initially, we often do that in terms of moles as well. which means that when we get a value for enthalpy, we have to divide it by the number of moles. Or in other words, our step one, as we look at material that we're working with, is we need to figure out how many moles we have using mass mole conversions often. And then we're going to take our value that we get for enthalpy and we're going to divide that by the number of moles. And that allows us to make more comparisons across various expressions in labs and substances and etc., because it standardizes us. Okay, so there are some problems with regards to this. Note that I provide a practice problem for you as well as the problems themselves. Okay, so our lab isn't going to serve as an example of doing this. That's a calorimetry lab, which you have received. And let's just talk about a little bit of things that you might need to know to do the lab and to carry out these calculations. So, background assumption number one, pressure is atmospheric pressure, so it is assumed to remain the same throughout the duration of this experiment. And this is, I'm just going to give you a little sidebar based on some of the content that's in your chapter that we're not going to go into great depth at. We're going to be working at constant pressure. It is also possible to perform these experiments at a constant volume. And you would still measure temperature change and you would still use very similar equations. In this case, you would need to carry your experiment out in a very rigid container so that you knew that there were no changes in pressure. No changes in volume as a result of the reaction. Okay, so we do have another background assumption. And that assumption, which is bore out, is that if we have a reaction taking place in a solution and the temperature of the solution goes up, that reaction is exothermic. And if you think about that for a minute, what we're saying is when the reaction is releasing temperature, it's going to go into the surroundings. The solution is serving as the surroundings, and the temperature of the solution is going to be increasing. Okay, and that similarly to that, then if we have the reaction taking place in the solution and the temperature of the solution decreases, that means the reaction is endothermic, meaning the reaction is absorbing the heat. And where does it absorb it from? It absorbs it from the surroundings, which happen to be the solution. Okay, and then the background assumption number 3, which holds true more for our particular experiment, would not be true in all cases, is that we're going to place this in water. If we are using water, it would always have a known specific heat capacity of 4.18 joules per degree Celsius times gram. Okay, so wrapping this up, and the key idea is the energy, which would take the form of heat, that's released by the reaction will equal the energy, again in the form of heat, that's been absorbed by the solution. The key equation that we're going to use in solving these is that energy, or enthalpy, is equal to S times M times T. Now here I've introduced S, which is another letter for specific heat capacity. I put it here so that we have a chance to sort of review again that you're not going to find consistency in the letters, unfortunately. So bear in mind that you may see C there instead of S. M would be the mass of the solution in grams, and T would be the change in temperature in degrees Celsius. Okay, and you can hopefully, what you'll see as you work through this experiment is that change in heat, again, it's going to be the same for both substances. The direction is going to change. In other words, one thing will be cooling while the other is heating. When the materials are different, the specific heat capacity is also going to change. And you may be given it, you may be calculating it. The mass of the solution is something which you can measure. So this is an equation that we're going to use in an experimental setting, and you're going to have the ability to measure the solution's mass as well as that change in temperature. Okay, and so there's a couple things to think about as you get started on this lab. What happens if the temperature decreases instead of increases. So what change? What does it mean? So the temperature of the solution we're referring to in this case, if it increases, what does that tell us about the system? Temperature solution increases tells us what about the reaction? But what if it then, instead of increases, it decreases? What is that telling us? That's different about the actual reaction. So when you look at the experiment, you'll see that there's a certain amount of the solution used. What happens if you use twice that much solution? What variables would you expect to change? So just think about, how does the amount of solution how does it impact other variables in the equation? And note that we are most concerned with the solution as a mass. That's what we use in the formula. You often measure solutions obviously in volume, but they can also be measured in mass as well. And then the third question to think about, is heat an extensive or intensive property? So here you may need to go back and look at a definition. What's extensive, what's intensive? And then think about which one would heat be. Okay, and then in preparation for our next class, you need to be reading the next few sections, 6.3, 6.4. I've just summarized the problems that were indicated throughout. The data table and lab calculations, those are going to come about as we do the lab. And I also recommend at this point that you pull out of this presentation and through your work with the problems, your key formulas again. Remember that you want to keep track not only of the different letters and what variables they represent, but you also want to keep track of the appropriate units. And if you find you need specific conversions, you should make note of those as well.